Sounds are everywhere. Close your eyes and just listen. Think of familiar sounds. What comes to mind? Birds chirping, lawnmowers in the morning, fire engines racing to a fire, rockets lifting off the ground. Could you picture those things? But what if we take away the sound? Sound is important to our daily lives. It helps us to experience the world around us. Without sound, things just don't seem right. Sound is possible because of vibrations. Something has to be vibrating, moving back and forth. Sound travels as longitudinal waves. We can demonstrate this idea with a slinky. The slinky is stretched out and one end is given a push. A wave is set in motion, and it travels the length of the slinky. Sound can only travel when there is something through which the vibrations can travel. Air is the most common substance through which sound travels, but actually, sound can travel through many things other than air. In some substances, sound even travels faster than it does in air. So how fast is sound? In air, it travels 343 meters per second, or 750 miles per hour. This is a little more than 1,000 feet per second. For comparison, a sprinter can run about 11 meters per second, or about 36 feet per second. Traffic on the highway travels about 30 meters per second, or about 98 feet per second. Here is a comparison of the speed of sound in different materials. In water, sound travels about 4 times faster than in air. And in steel, sound travels almost 15 times faster. Can you guess why sound travels faster in liquids and solids? Well, think about the atoms and molecules contained in gases, liquids, and solids. The particles are closer together in liquids and solids, so sound can travel faster because the particles can hit each other more easily. When you watch a fireworks display, you see the explosions before you hear them. Which travels faster, sound or light? Well, think about another situation, like a thunderstorm. We see the lightning and then hear the thunder. Light is actually much faster than sound. Light travels 300,000 kilometers, or 186,000 miles per second. That would be like traveling from New York to San Francisco 62 times in 1 second. Sound, compared to light, is barely moving. When an object vibrates, it disturbs the air molecules around it. The molecules carry the energy of the sound in all directions. The sound travels out as waves. Think of a wave in water. If we drop a pebble into a pond, the waves move out along the surface from where the pebble hit the water. Sound travels in longitudinal waves like these, but in all directions. The vibrations of the sound disturb the air molecules. In outer space, where there are no gases, sound would be impossible. The emptiness of space is called a vacuum. There are no molecules of matter for sounds to move through, so in outer space there are no sounds. 2 things are needed for making sounds: vibrating matter to create the waves, and a medium or something to carry the sound waves. We can receive sounds over great distances when we use a telephone or when we dial up a radio station. When you use the telephone, a small microphone in the telephone changes the sound of your voice into electrical signals. This signal travels to the person with whom you are speaking and is changed back into sound when it goes into a small loudspeaker in that person's phone. Along the way, between the 2 people, the electric signal may be carried through wires, changed to radio signals and sent through the air, or even changed to light to travel through fiber optic cable. This flashlight has been altered so it can show how light can be used to transmit sound. This solar cell picks up the rapid fluctuations and the brightness of the flashlight bulb and turns it back to electrical pulses. may have noticed that sirens sound high-pitched when coming towards you, and then when moving away, the sound is lower-pitched. This effect is called the Doppler effect. It is explained that as the sound approaches, the waves are pushed closer together, causing a higher-pitched sound. When the sound is moving away from you, the waves are further apart, and the sound is lower. Here is a tuning fork. When we strike it, it gives off a certain tone. If we could see what is happening, it might look like this. The tuning fork is vibrating. As the prongs move out, they push against the air molecules around them. The molecules push together, which is called compression. Then there are places where the molecules are spread out between the compressions. This spread out section is called rarefaction. The whole sound wave travels as a longitudinal wave, so compressing some molecules and leaving areas between the compressions with fewer molecules carries the sound. The slinky is pulled and held across the floor. We pull together some of the slinky sections and then let it go. Notice that it travels the length of the slinky with areas of compression and rarefaction. Remember that sound needs a material to travel through. The rate of vibration is called the frequency of the sound. Frequency is how many times the sound vibrates in a certain amount of time. Frequency is measured in a unit called the hertz, after Heinrich Hertz, who demonstrated the existence of radio waves in 1886. 1 vibration per second is 1 hertz. 2 vibrations per second is 2 hertz, and so on. Humans can hear sounds that range from 20 to 20,000 hertz. That means we can't hear sounds that have frequencies less than 20 vibrations per second, or greater than 20,000 vibrations per second. Sounds below 20 hertz are called infrasonic, and those above 20,000 hertz are called ultrasonic. Even though we can't hear above 20,000 hertz, there are other animals that can. For instance, we can't hear a dog whistle because the sound is so high, but dogs certainly can hear it. The dog whistle produces a sound at 30,000 hertz. Here is a chart of the frequencies some animals can hear and produce. Notice that the bat and porpoise have huge ranges of sounds that they can make and hear. That's because they use their ability to produce and hear ultrasonic sounds to help them find things. You can tune in radio stations because each station is given a certain frequency that they can use for transmission. The station sends its signal as a radio wave that corresponds to a certain number of vibrations per second. On the AM dial, the frequencies are measured in kilohertz. This means that if you dial to 940 kilohertz on your radio dial, then the frequency of that station is 940,000 vibrations per second. On the FM dial, everything is measured in megahertz, so the frequencies are even higher. Remember, humans can only hear up to 20,000 hertz, so these signals are well above what we can hear. The signals are out there all the time. All we need is something to convert them to sounds we can hear. The bat hunts by sending out an ultrasonic signal that bounces off an insect and returns to the bat's big ears. The bat can determine the exact location of the insect and catch it in complete darkness. He doesn't use his eyes, he uses echolocation. The high-pitched sounds he makes bounce off things and return to his ears, creating a picture of what is around him. Porpoises and dolphins use echolocation to swim in murky water or to locate objects in the water. The best conditions for an echo are when a sound strikes a hard, smooth surface. The sound is reflected or bounces off the surface, and we hear it again. Echoes and sound reflection can cause problems in certain situations, such as at a movie or in a concert hall. To cut down on reflected sound, materials are used that help absorb the sound. In a movie theater, they use carpeting, drapes, and padded seats. In this recording booth, the walls are soundproof and covered with cushioned material to deaden the sound. Sometimes we need to get the sound reflected out to a large area, so curved surfaces are used to bounce the sound out to the audience. Reverberation is the repeated reflection of sound waves against smooth surfaces. That's why sounds in a gym seem to echo and sound strange. Another problem is called interference. This is where two sounds come together. If they come together at the same time, and their compressions and rarefactions match up, the sound is strengthened and becomes louder. However, if the compression of one wave hits the rarefaction of the other, they cancel or wipe out each other, and there is silence. That's why when people design concert halls, they try to consider the reflection of the sound and how it will produce reverberation or interference. Sound can be measured in terms of loudness. To do that, we use an instrument that measures the loudness of sounds in units called decibels, which are abbreviated dB. A soft sound is rated as 1, and a loud sound is 120 decibels. This meter is used to measure the loudness of sounds in decibels. Here are some examples of common sounds and their decibel readings. Breathing is rated at about 10 decibels. Talking is 30 to 60 decibels. A vacuum cleaner is 60 to 80 decibels. Motorcycles and subway trains are from 70 to 90 decibels. Thunder is 95 to 115 decibels. A rock band is about 110 decibels. And a jet taking off ranges from 120 to 140 decibels. Humans will experience pain when decibels reach 140. Exposure to loud sounds can cause hearing damage and even loss. People who work around loud machinery need to wear protective ear gear. We hear sound waves passing through the air with our ears. The outer ear helps to collect and direct the sound waves to the tube leading to the middle ear. The middle ear is called the eardrum, which is a membrane that vibrates with the pressure changes caused by the sound waves. The eardrum is attached to several tiny bones. They are called the hammer, the anvil, and the stirrup. They amplify or increase the sound. The bones are attached to the cochlea in the inner ear. The cochlea is filled with a liquid that changes the signal to an electrical message. The message is sent to the auditory nerve, which goes to the brain. The brain then interprets the sound. Music is an important and enjoyable part of our lives. Music is different from noise because music is made up of regular patterns. Music has pitch, rhythm, and quality. Pitch has to do with the frequency of vibrations. Close vibrations produce high notes, and spread out vibrations produce low notes. Rhythm is a regular pattern of tones. The quality of music is made up of the different tones. We can use this oscilloscope to look at an electrical representation of sounds. This electronic keyboard is connected to the oscilloscope. When we hit a key on the keyboard, we can see the picture of the wave pattern. The high points are called crests, and the low points are troughs. The distance between one crest and the next crest, or from one trough to the next trough, is called wavelength. If we play a low note and then a high note, you can see how the frequency changes. Low notes have a frequency that is spread out, and the wavelength is greater. A high note has wavelengths and a frequency that are closer together. Notice that if we change to a different instrument sound, The result is a wave pattern that is different in shape. The piano and the trumpet keyboard sound have different wave patterns. The oscilloscope is helpful when analyzing and studying sounds. There are three categories for musical instruments, called strings, wind, and percussion. Each type of instrument must be able to set particles of air into motion. Again, vibration is the key to sound. With stringed instruments, the string is plucked or stroked and begins to vibrate. The hollow part of the instrument helps to increase the volume of this vibration. Here is an example with a tuning fork. We strike the fork and the sound given off is faint until we touch the fork to the sounding box, which increases the volume or amplitude of the tuning fork. Wind instruments rely on vibrating air inside the instrument to create the tones of the instrument. Sometimes the tones are changed by covering and uncovering holes that make the column of air shorter or longer. Sometimes the instrument creates the sound by changing the length of the air column, such as the sliding U-shaped tube in and out on a trombone. Percussion instruments can make music when a stretched membrane is struck with a hand, stick, or mallet. The stretched membrane is tightly attached to one end of a frame. When the membrane is hit, it sets the air to vibrating in the frame. Different sized frames produce different sounds. Of course, you don't need expensive musical instruments to make your own interesting sounds. Things from around the house can be used. Here are some examples. The first one is made from a section of plastic tubing. Twirl this around your head and notice the strange sound. Whirl it faster and faster to hear the sound change. You can get a wine glass to sing by pouring about an inch of water into the glass. Then wet your finger and rub it slowly and gently around the rim of the glass. Be sure to hold the glass with your other hand so it doesn't tip over. Try different amounts of water in the glass to see how the sound changes. Make a guitar from the material shown. The eye screws are used to tighten the fishing line so that you can get the air vibrating. Make different notes. Move your finger up or down the neck of the guitar and hold the fishing line down to make it shorter or longer. Short line is high-pitched and long line is low-pitched. Stretching material such as plastic, paper, or rubber from a balloon over different containers can make drums. Try large bowls and even cardboard boxes and tubes. For a wind instrument, try different lengths of an old hose. We get great sound from laser discs, such as CDs and DVDs. Laser discs carry digital information. That means the information is represented by the ones and zeros of the binary code. Any number can be represented in the binary code. For instance, the number 1 is represented as 1. The number 2 is 10, and the number 3 is 11. Laser discs are made up of microscopic pits. The pits represent a 0, and the spaces that don't have a pit represent a 1. A laser beam is directed to the reflective side of the disc and responds to the pits or pitless areas. So the laser beam is focused on a very small part of the disc. If it hits a flat, pitless area, the laser beam is reflected back to the detector and is registered as a 1. If it hits a pit, then very little of the light is reflected back to the detector, and it is registered as a 0. The laser never touches the disc, just a beam of light, and because it has a clear protective coating, the disc will not wear out. Sound is an important part of our lives. We collect information about things around us by listening. We are relaxed and entertained by music. Or we rely on sound to get our ideas from one place to another through the use of telephones. Sounds are important in the animal world, too. Some animals use ultrasonic sound to catch their food or find their way. Others use sound to send out warnings of danger. Some use sound to call to each other or to signal that this is their territory. However it may be used, sound is a major part of our daily routines. Now it is time for the program quiz. Here are 8 short answer questions. Question number 1. Which travels faster, sound or light? Question number 2. Sound travels at different speeds in different substances. Why does it travel faster in metal than in air? Question number 3. How do animals like bats or porpoises use ultrasonic sounds to find their way or to catch food? Question number 4. In outer space, there are no sounds. Why? Question number 5. The hertz is used to measure the frequency of sound. If something is rated at 150 hertz, what does that mean? Question number 6. What is an echo? Question number 7. What are 3 primary types of musical instruments? Question number 8. What is a decibel?